introduce myself and my co-host Noah. My name is Eric Johnson. I'm a firmware solutions engineer at Memfault. Previously, I've worked at companies like Walgreens Health and Athos, doing a lot of embedded device development, particularly around BLE in my case. You can find me on LinkedIn, and I'm also working on some future interrupt posts as well. And I'll turn it over to Noah.
Hi, everyone. I'm Noah Pendleton. I'm also a firmware solutions engineer here at Memfault. I've been doing embedded software engineering for the past 12 years or so. Worked at companies like American Power Conversion, Markforged, and Fitbit, debugging all sorts of like weird and wacky field issues. Fitbit was fielding millions of devices, so we were looking at like folks doing all sorts of strange things, like syncing their watches with an Xbox as an example that comes to mind. And so, yeah, this webinar is going to be pretty awesome. We're going to be talking about some like strategies for debugging those weird field situations. You can find me on Twitter, although I'm not very active, as well as LinkedIn, and I try to post on that interrupt blog of ours. So go and check those out if you're interested.
Awesome, thanks, Noah. So just a quick overview of what we're going to be discussing today. We're going to start off with what a traditional debugging workflow looks like, particularly focusing on local debugging and logging. Then we're going to move on to how does Memfault fit into all this? How do we increase your visibility into your device when a fault happens, and kind of all the unique things that we bring to the table that traditional debugging can't give you. We'll then go into some trickier problems that Memfault is able to capture and help you analyze. And then finally, we'll cover the concept of offensive programming and how that paradigm fits in with Memfault. So to start off, just trying to get a feel for what everyone's background is, we have a poll to start off. And the question is, do you use step debugging or local debugging or printf debugging, throwing in some printf lines into your code while you're trying to solve a problem? And we'll give this about 30 seconds or so on this poll. Okay, awesome. Thank you for that feedback. So based on this, practically everyone here uses one of these two techniques in their debugging workflow. So now that we have kind of established that, let's go into what this looks like in practice, just so that we're all on the same page as to what the typical debugging process looks like. So, local debugging, we all know this. This is a very common feature of different IDEs that people use. In the screenshot, we're showing a clip from VS Code. But local debugging is great for stepping through your code, trying to figure out, is this code path taken or not in certain scenarios. And it also gives you a pretty clear view into the state of your device. You can see local variables, you can see different thread states, things like that. An additional tool that we all love and know and love is to throw in a printf whenever you're trying to figure out, did something run, or what the value of a variable is. Lots of RTOSs also provide logging subsystems, so you can kind of get a nice format to your logs, note which component the log came from. And the nice part about logs is that all it takes is a serial terminal to get these out. And from here, I'm going to turn it over to Noah for a short demo on local debugging.
Awesome. Thank you very much, Eric. All right, let me just share this session here. Okay, so what we're looking at here is, it should be pretty typical of like any IDE workflow. The particular setup that I'm using is VS Code with Nordic Semiconductor's NRF Connect set of plugins, which provides like a whole bunch of features specific to the NRF Connect SDK. So what I've done is I've got a board on my desk. This happens to be a NRF52 development kit board plugged into my computer. I've got this IDE set up, installed all the tools, et cetera, et cetera. And then I picked out an example app to run. This is the peripheral MDS example app from the Nordic Connect SDK. So it's a pretty nice example here to show because it uses like a ton of subsystems in Zephyr and the Nordic Connect SDK. Bluetooth systems are running, flash file systems, bootloaders, all sorts of stuff is going on. And it also has a nice UART terminal that is routed over that same USB connector. So I can use that USB terminal to both view the logs that the device is generating, as well as interact and run some test commands. So this should all be pretty familiar to folks who have done this sort of thing before. So what I've done is I've got this IDE all set up and configured. I've pressed the debug button to flash the board and start the debugging session. And what we've got here is my main program is started and there's the program execution is halted right after main. The other thing I'm going to do is I'm just going to start a serial terminal on the UART of the board, so we can both see the logging statements that are being generated by the program, as well as interact with it if we want to. And now that I've opened up that serial terminal, I'm just going to reset the debugger here. Okay, there we go. And so, yeah, what we see is, the same thing happened. The board reset. The bootloader printed out a few things saying like, booting Zephyr operating system. And then we're jumping to the first image slot, and then it halts at main, program execution halts at main again. So yeah, typical, step debugging, you might set a breakpoint, you might start your program execution again. So there we go. Our program's now halted at this point on this particular line of code. And we can see this, this IDE provides like a lot of nice features that you may be familiar with. It's showing like local variable values. Also has a nice breakdown of all the active threads in the system. So it looks like we have about 5 or 6 running threads that are currently sort of not doing a whole lot of interesting stuff, but you can see the backtraces here. It's also pretty nice. It lets you hop into those different threads if you want to inspect some state there. So that's pretty handy. And we see there's some print statements and such. So if we just resume program execution now, yep, we can see, okay, great. Our UART terminal is here. We can run some commands. So maybe I want to inspect, run some shell stats command here. Okay, there's 0 loss logs, that sort of thing. We also have the Memfault demo CLI, so we can run crashes and stuff like that if we want to test things out on the Memfault side of things. But what I'm going to do is I'm just going to press the pause button here, which will halt program execution. And that's just going to halt the program at whatever instruction the CPU happens to be running at the point where I press that button. In this case, we're running an RTOS, so it's just in this wait for interrupt sort of idle state, which is pretty common for an RTOS that's not busily doing stuff. And what we can see here is, the similar sort of thread state that's being shown for us, which is really handy. And maybe we want to go and inspect some other status or whatnot, while we're debugging this program. I'm just going to resume execution again. And okay, something bad happened. And the reason I'm showing this is I want to give an example of problems you might encounter while doing local step or interactive debugging. Basically, what was going on in our system, we had a lot of subsystems running, and some of them had tight timing requirements. And specifically for this program, there's a Bluetooth subsystem that's running, and it needs to be serviced frequently. And when it doesn't get serviced, that subsystem generates an assert. So it says, I didn't get serviced in time. I'm going to crash the system because something was broken. And we end up in this sort of halt if debugging shim, which is it's a pretty handy thing to have if you are doing step debugging. Basically, if the debugger is attached, we're going to hit a breakpoint here and automatically stop, so we can figure out what was going on while our debugger is attached. But this is just showing that when you are doing interactive debugging, it can be pretty intrusive to the system and cause problems. That you'll have to figure out workarounds. Maybe you'll have to disable your watchdogs while you're debugging. Maybe you'll have to alter how some subsystems work, removing timeouts or other things. Or maybe it just won't be very practical to use step debugging or interactive debugging comprehensively in your system. All right, I'm going to pass it back over to you, Eric.
Thank you very much, Noah. So Noah just highlighted one of the ways that local debugging it doesn't cover all the scenarios that you might hit, especially when you're trying to work through a particularly tricky bug. Some other things that you might hit is you don't have access to your device. It is sealed up in its plastics, or I personally worked on a device that was meant to be waterproof, so opening it up was broke the seal and we couldn't get that back after that happened. Log analysis is particularly difficult because logging is unstructured. It's a pain to write a lot of regexes to pick out specific tokens in your string just to then analyze them afterwards. And then finally, as Noah highlighted, local debugging is extremely invasive to the system behavior. You're halting the CPU. Timers are not necessarily aware of that. And so you hit all these assertions and tricky things like that. So, now that we've kind of discussed where these shortcomings are coming from, we'd like to ask you guys, how often have you hit these shortcomings? And so our next poll is here, and I'll go ahead and launch this. So our question is, how have these techniques failed you in the past? We have 4 options: devices failing without an attached debugger, printf information not being sufficient, crashes being missed, or any of the above. We'll give this a few more seconds. Awesome. Thanks everyone for voting there, and I will share the results briefly because I think this is interesting in that everyone kind of hits all of these problems. They're very common, and there's lots of scenarios where they occur. So it's tricky when you don't have any tools beyond these techniques. But never fear, Memfault to the rescue. We can give you more insights and can work in these tricky scenarios where you don't want to modify system behavior. So the way that we do this is primarily through a few features, and the first of which I will focus on is core dumps. And I'll start off by explaining, what a core dump is. So a core dump is a saved kind of view into your system state. We collect the firmware version that you're currently running, things like the time that the fault occurred at, the device serial number, hardware revision, but we also collect memory regions. And what is a memory region exactly? Well, we focus on a few things, such as the active stack of where the fault occurred, the state of the other running tasks or threads on the system, and then we can from there move on to more targeted memory regions of memory. Say you've got a data structure that's of interest when a crash occurs, or we could do something as broad as all of BSS. The other tools that we provide are metrics heartbeat. So this kind of gives you a runtime view into the device. And so you can track kind of performance characteristics like how long your main task is running, the state of your heap, and how many bytes are free in it. So very, metrics measure different characteristics of your system as it is operating. And this can kind of help you determine the cause of a fault leading up to it occurring. So how do we do all this? I'll start off with talking about our SDK integration. In this case, I'm focusing on the ARM core architecture, but we also support a few others, and we'll go into that later in the talk. But with ARM, we hook into the standard fault handlers, such as hard faults or usage fault, and we route these to our main fault handler, the Memfault fault handler. This fault handler is responsible for saving the core dump, so it will go through, collect all those memory regions I mentioned previously, save them into your non-volatile storage or potentially RAM if you don't have access to that, but flash is best. And then on the next reboot, our SDK will take that core dump that we collected, chunk it up into packets that you can then send on their way up to Memfault for analysis. The other piece of integration that fits into what we've been talking about today is our logging integration. So we do this through 2 different methods. The first that I'll talk about is if your RTOS provides an existing subsystem for this. In the case of Zephyr, we register as a backend. And so what this does is you can use the typical logging macros that Zephyr provides, like log info. That'll get calls into the Zephyr logging subsystem, and then it sends the log message both to our backend, which is implemented as a circular buffer, and any other backends you might have registered, like say your UART console. The other option is to hook into your existing logging functions. So we provide a simple function called Memfault log save. You give us the logging level of the log and the formatted string, and we'll take care of the rest, again, saving that into that circular buffer that I mentioned. So kind of exciting time now. We are going to go into some demos. And I'm going to start off by pulling up the Memfault web app. And right here, I've got a device that I've been using. It's a ESP32 dev kit, as seen in my video. But it's so it's an extensive architecture, another architecture that we support. And in this dev kit, I've kind of got an example running of a touch controller driver. This driver periodically receives input from a touch sensor and does some processing on it. And what we're looking at here in this device page is our timeline of my device. And so we can see basic characteristics of it, like which software version it's running, when it was last seen, things like that. And the timeline view contains a lot of information. What it does is it's aggregating each of these traces into a single view, or sorry, each of these tabs into a single view, and gives us like a nice summary way of looking at the device's operation over a period of time. So we can start by, we'll focus on the metrics that I've recorded for this device. I have 3 metrics that I'm displaying. They are I'll also add, I'll switch to bytes free. So the Heap bytes free, the touch controller reading error count, as well as we have a timer running to measure how long over each interval were we connected to Wi-Fi. So we can see our device starts operating on the left-hand side here. And our Heap is starting off at a level of, looks like 140K bytes. But unfortunately, we're seeing a not good trend on our Heap level. It's decreasing over time, which is pretty indicative of a memory leak. We can see that our touch controller's errors are kind of varying, but they're relatively constant. So that's probably something we want to look into. And also not great, our Heap is reaching a level, we seem to drop off of Wi-Fi connectivity, and ultimately we then hit a hard fault here. So, this looks like a memory exhaustion issue, and we collected a core dump in this case. So now we can check this out and see what sort of info Memfault can provide in these scenarios. And this is an example of a core dump that has been analyzed by Memfault. So what you can see here is kind of the same visibility that we had in Noah's local debugging demo. On the left here, we have the state of each of the threads that was running. The top thread is the thread where the fault occurred. In the middle here, we have different panels showing what the state of variables in your registers and locals are, as well as any additional memory regions that we collected. So that might include like your global and static variables. So in this example, we think it's, memory related. So we'll start there. We think that it's in our touch controller based on those errors that we are seeing in our metrics. And the other thing that I should touch on is that we, in our device, we also were collecting some logging. And let me switch windows. And each of those logs were sent up here, and we can take a quick look at these. And so we do have access to our logging just like we would if we connected our device up to our serial console. So we can see a touch reading, some checks for OTA. And here's some failures to read our touch sensor. So, okay, that gives us a little bit more info as we're looking at this crash. And let's dive into the thread where the crash occurred. So our touch controller thread, I can, just like Noah was showing before, I can move up and down in the call stack. And if we go to the function where the error occurred, we can see, okay, I would guess that it's not great that our read buffer is null. So I think that tells me that this is some sort of memory exhaustion error, could be in our touch controller, and this is what caused our fault. So I'm going to turn it back over to Noah, and he's going to go through some additional examples.
Awesome. Thank you, Eric. Okay, so I'm going to go through a few other sort of issue categories that Memfault will analyze for you. So I've just opened up the Memfault dashboard here, and I'm just going to go down to the issues list and click on this hard fault here. Before we do that, I just wanted to highlight a few bits of breadcrumbs that are shown in this issue list. So we can see, which software version it's running on. This is, affecting these two, it looks like, or this range of software versions, when it was first reported and most recently reported, and the number of reports we've seen, which is 2 on a single device. But if you have like the same sort of issue occurring on multiple devices, you'll see that device count increase and whatnot. And then you can use that to prioritize fixes that are affecting like a lot of devices, or maybe like one device is just being problematic. All right, so if we dive into that detailed issue view. Yeah, it's very similar to what you saw on that other chip that Eric was showing, but that was, of course, an ESP32 Extensa architecture, whereas this, we're looking at NRF52. It's the same board that was on my desk. This is an issue that it uploaded previously. And this particular crash is an ARM Cortex-M hard fault exception. So automatically instrumented by Memfault, scooped up the crash data, and Memfault did all this analysis to generate this view here. Looks a lot like our IDE, just like Eric was showing before. We have great breakdown of all the same threads that were running in the system. So just like when we were looking at it in a local debugger, we can do the same sort of stepping through the different thread states if there's some other thread that we want to look at. It's also nice that it highlights like what's going on in these threads, whether the idle thread is ready to run, these other ones are blocked on various queues and whatnot, which is pretty typical. And the main thread is actually exited, which is cool. If we look at this actual crash analysis that's being done here, it is a hard fault, and we're doing some breakdown of the exception status registers. So this particular fault was due to a loader store along a non-word align location, which is an illegal operation in this particular Cortex-M4 architecture. This fault was generated like artificially using the Memfault test CLI. But we can actually see, this error occurred at this Memfault demo panics.c file. So we could go directly to that line and check it out and see, okay, yeah, there was like, this illegal operation that was being generated there. And these types of errors, they do happen in the field. Typically, there's some weird aliasing or some sort of like, memory addressing that's like been, a little bit misconfigured. Maybe like a weirdly performing peripheral has like specific memory requirements, that sort of thing. I'll also highlight that this particular crash, did occur twice on the device. So we can go and look at like older traces. Memfault does this automatic deduplication. So multiple crashes from like the same device or the same crash occurring on multiple devices, they'll get aggregated under the same issue. Then you can click around to see, a specific trace instance, and you can even download it and analyze it offline too, if you want to do that. And this particular crash, we're also doing some automatic analysis of the stack high watermark. So you can see, like, for example, in this shell UART, we can see there's, about 1.3K free. So that's pretty nice. And maybe we could even like downsize that, that stack, because we have like over a kilobyte of unused space there. But if one was like tighter, it may be like a good signal that you need to increase the thread, excuse me, the thread test size, stack size. All right, the next fault I'm going to show is a stack overflow fault. So this is also on a Zephyr RTOS-based system. And Zephyr RTOS has pretty nice instrumentation options available. So you can enable the stack overflow guard in Zephyr RTOS, which is super cool. What it does is it sets like a memory protection region right after the stack of every task when it gets switched to. So if you happen to try and access memory like just off the end of that stack, it'll trip a fault, and Zephyr will actually like enumerate it as a stack overflow, which is sweet. Like it points you right to the error. The fault occurs exactly at the access that caused the fault of the error. you don't have to like go chasing down some weird like unrelated symptom. Yeah, so it's a great feature, and Memfault does support analyzing these types of crashes. And we can even see, okay, yeah, our stack watermark is showing like 0 bytes free. We ran out of stack, overflowed. That's bad, and we don't want to have that happen. So maybe we need to increase our stack, or maybe we need to look at, what was going on at the point of failure. So yeah, we're in this like compute FFT function here. And the sample count here looks like kind of egregiously high. So that may be indicative of like some computational error or something, maybe a malformed data error, some integer overflow or something like that. So you can go ahead and use this information to try and maybe fix the fundamental problem in this system. The next fault I wanted to show is a watchdog fault. So I think this is really, really cool. So watchdogs are a huge pain in the butt. They can fire due to like conditions that you had no way of predicting when you were like doing your beta test or your bench testing. These devices get onto the field, and some Wi-Fi router it's connecting to like has some like weird problem with it that causes like some watchdog to fire in your system. So what's great about Memfault is you can hook it up to your watchdog handlers, and it'll snapshot the state of the system when the watchdog fired. So you can see exactly what the system was doing when when that watchdog timed out and tripped. In this case, we can see the active stack at the time, or the active backtrace at the time of failure. So we're in this sort of spy flash erase function in the spy.c. If we go ahead and look at that, we can see, okay, we have some iterator variable here. It's a pretty high value. We probably don't have like a 40 gigabyte flash attached to our system. So that's a good indication that there's something probably problematic in that routine, maybe a similar type of arithmetic error. All right, I'm going to pass it back over to Eric to show a few other errors.
Awesome. Thank you, Noah. And keeping on the theme of watchdogs, we have a slightly different variant here. Our SDK provides what's called a task watchdog. And the task watchdog is a component that is used to measure when other tasks in your system might be stuck. So say you have a BLE task that's running and a connection attempt is taking too long. You can use the task watchdog to catch those type of lockups in specific tasks. So the rest of the system might be running, but one problem task is stuck. In this case, we've implemented our task watchdog, which is provided as part of the Memfault MCU SDK, but other operating systems also provide their own Zephyr, I think either FreeRTOS or ASP.IDF. So definitely check those out. They're very handy to have, especially when you're running in an RTOS environment. So diving into this specific core dump that we have, one thing I'd like to highlight is that we just added RISC-V support. And so we support RISC-V on the ESP32C3. That's where this core dump was captured from. And so let's take a look at since we are focusing on the task watchdog in this example, let's focus on our threads or tasks. We can see that we have our timer service, which is our task watchdog here, and we've caught an assert. So that's great. We know that our task watchdog fired, and one of the tasks in our list was blocked when it shouldn't be. So we can take a look at using our globals and statics view, and I'm using this filter to pull up the information on our task watchdog. So we have this global variable that contains the information on which channel caused the task watchdog to fire. And if we expand this out, again, this is just like our view in a local debugger, which is pretty amazing. Just not having to do this on your own, we provide all of this out of the box. The thing that we can see here is that it was channel 0 that caused the task watchdog to fire. And I happen to know that channel 0 is this example task here. And if we expand our example task, we can see that, Yeah, we definitely screwed up in the way that we were taking some locking primitives here. You can see that we take a mutex and we follow that up immediately by taking a semaphore in a blocking fashion. So this thread locked and got stuck, and that caused the task watchdog to fire. The next issue that, or really tool that I'd like to highlight, I'm going to go back to the touch controller example that I discussed in the beginning of our demos. So we were talking about how, we think that this is a dynamic heap, allocation error where we're draining our heap over time. There's some sort of leak in our controller. And so we have a feature that you can enable called our heap tracer. And this tool is used to trace through each of the allocation calls on your heap. What we do is we wrap your system's malloc, or in the case of Zephyr, we wrap the kernel heap through kmalloc, and we record the address of the allocation, so you know where in your code this memory was being allocated from, and then we record the size of it. And so what I can show here is, we've got this long list of all these heap memory allocations. And again, this is running on ESP-IDF. So we've got a Wi-Fi stack running, we've got an IP stack running, and we've got, at least my example task that's getting touch controller readings running. So there's a lot going on here, and we can see that in our heap trace. And a really nice feature is that we can kind of aggregate by where this memory is being allocated from. So I'll click on this here, and now we get a very direct view into where all these allocations come from. You can see, a lot are coming from an HTTP client. If we jump in here, it's a little bit hard to read, but LWIP is allocating some memory as well. That's our IP stack. So that is very useful, getting some runtime state from your application to try and think about like how your memory utilization looks like. And then finally, getting back to the issue that we were talking about before, we're kind of allocating a decent chunk of memory, 4K, from our touch controller, and we can see that was recorded here. So the heap analyzer, the heap tracing, really kind of gives you some visibility into a structure that's notoriously difficult to debug. With that, I'm going to turn it back over to Noah.
Awesome. So the last demo that we'll show today is going to be around offensive programming. And so to give a little bit of background on this sort of notion of offensive programming, there is a great webinar by Tyler Often, one of our co-founders here at Memfault, talks in detail about this strategy, like what it can do for you, and really good ways to utilize it in your system. But fundamentally, what offensive programming is you add proactive checks for errors in your system that you don't expect to happen, and should they're a signal of like a catastrophic problem in your system. So for example, and it's typically implemented with like an assert macro or like some sort of like, intentional crash check. And so, yeah, that's a super powerful technique. Like you can, actively, have your system monitoring itself for problems that, you really want to detect before they get into a customer's hands, or even when the system is in a customer's hands, some, catastrophic issue that you want to get like a super good, memory trace and all this detailed debug information out without the customer having to call you up and say, hey, my door lock reset and like it's not responding, like what's going on. So yeah, really being proactive on that stuff can be a super powerful tool to help you like narrow down these types of nasty bugs. And so a couple of examples of that that I've shown here on this slide. So very traditionally, if you malloc and there's no room left in your heap, you're going to get like a null pointer, like the malloc failed. And what you can do is you can assert on that malloc, and some allocation libraries actually provide like an option to enable this, within their allocator itself. But basically, what you do is you check that the allocation is succeeded, and if it failed, you consider that a catastrophic failure, and then you're going to get a really nice backtrace that points you right to where the allocation failure occurred. You don't have to like chase down, maybe there's some knock-on effects when an allocation fails that that really makes that debugging process, really challenging and difficult. So that's a pretty awesome technique there. And that sort of technique would have helped, to tie it back to Eric's example with the touch controller that's like got an allocation leak. that would have really helped that problem there, because it would have, given you that core down right at the point of failure, rather than having to sort of like do this heap tracing, sort of click through a bunch of like information. It's amazing that we have that information available, but it's even better if we can just get a direct pointer right to the problem site and fix it, really quickly. The other example I have here on the right is a double free error, and these definitely happen in the wild. You'll see plenty of CVEs out there, on problems due to double freeze. And what's really cool about double freeze specifically in Zephyr RTOS, although this applies to like other allocation systems as well, but in Zephyr RTOS, there's an option you can enable to trap double freeze. So this is the case where you have allocated some dynamic memory, then you free it, and then you accidentally free the same pointer again. That can like be pretty destructive if some other subsystem has gone ahead and allocated at that same pointer site, because then you would be freeing someone else's memory. And in C style language, there's no protection against that sort of ownership problem. So this double free protection is really cool. What it does is if you ever try and free a pointer that's already been freed, what Zephyr will do is it'll fire a runtime assert. And that'll point your crash right to exactly where the problem occurred. In this backtrace you're seeing here, it's just sort of artificially generated via like a CLI command. But you would see the exact same thing if if it happened in a real program, which is really, really cool. Those can be like super nasty, subtle type of issues where various subsystems are stomping on each other's allocations. So yeah, that's a pretty cool technique. And Zephyr RTOS has a lot of options around like detecting these types of failures at runtime, which is I think super cool. All right, that's it for the demos today. Now we're going to switch to the Q&A session.
Awesome, and I've got our first question just picked out. So this came from our webinar portal on signup. So one thing that this customer is asking about is, what do we do for devices that don't have internet connectivity? Say, what's the route up to Memfault from there? So
yeah,
do you want go ahead?
Oh, that's a great question. I'm sure Eric, you have a great answer for it too. Yeah, so Memfault is designed to like fit into these types of devices with like varying levels of connectivity. So we showed a few examples today, like ESP32, when it's connected to Wi-Fi, has like a direct link to the internet typically. So it can just be uploading data directly to Memfault. And that's super easy, like very nice, smooth workflow. But the NR52 board I have, that has BLE. It doesn't have like a direct connection to the internet. It needs some sort of intermediate gateway device to upload data. And then there's also devices that go for really long periods or maybe never have a connectivity path to the internet at all. And so Memfault was definitely designed with those systems in mind. We support like a very like flexible backend for storing data. So those core dumps, metrics, all that data can be stored on the device in various ways, whether that's like in some RAM buffers or into like some durable flash storage. And then whenever the device has connectivity, or even if the device has just like been RMA'd and it's on your desk, you can then suck out all that data, push it up to Memfault, and all the analysis can be done at that point. So there's no requirement on like data being directly uploaded from the device or data being uploaded in a timely manner or anything like that.
Our next question, so I'm gonna read this. So this question is, asking, is there a way to tell from our website, from the web app, if cloud processing has failed or like if there's some mismatch, because sometimes you might upload the wrong ELF file. You're doing a lot of builds at your desk. And the answer is yes. We have a little on the issues page. There's a queue status button at the top, and you can see if there's any issues that we encountered while processing your ELF file.
There's also, I believe, a API that you can hit that will provide the same information. So if you wanted to query like more proactively for any like sort of processing failures, you could also be doing that like on your own. The next,
go ahead.
Did you have one ready?
All good.
The next question I see here is our devices can only respond to access requests and cannot send packets on its own. Is the Memfault SDK able to store and respond with Memfault data on requests from a controller device? Yeah, so this is like a pretty typical setup for some of these IoT devices, right? They're not in control of their connectivity pathway. Instead, they rely on some host, whether it's like USB or BLE or whatever. And yeah, it's totally set up that way. Actually, that peripheral MDS example that I was showing earlier, that's how that works. So it sets up a BLE. It's a peripheral device, a peripheral BLE device. Relies on the host device to like drain the data off it via its like GAT characteristics that it sets up.
Our next question is asking about support for embedded Linux targets. So we do support embedded Linux. I would direct you to our documentation page for that, just because we don't have time to cover that today, unfortunately.
But I will say all the features we showed today, you're going to get like almost exactly the same experience on embedded Linux as well as Android. Yeah, all the logging, core dumps, and the metrics. And especially I will point out the metrics on Linux out of the box are really nice. You get like a ton of stuff because the Linux kernel provides like a lot of statistics about the system, CPU usage, that sort of thing. Here's a really good question. Are there more or less features supported on different RTOSes? Which RTOSes have full support? Great question. So if you're in an RTOS free environment, like a bare metal environment, Memfault, of course, supports that very well. And if you just won't see like, multiple threads because there wouldn't be multiple threads on your system. You just see the active task that's running. In terms of like, are there more or less features supported on different RTOSes? Memfault supports decoding a lot of RTOSes, and we primarily support, Zephyr, FreeRTOS, ThreadX. We have support for like ChibOS and TI-RTOS. Our best support is going to be, and so you'll see thread decode, but it generally relies on like a full memory capture. So you need to capture all the data for all the threads that you're interested in decoding. Whereas for Zephyr and FreeRTOS, we have like sort of more sophisticated ports that enable like a lot of that deep analysis of the various threads without having to capture like vast amounts of memory. And what that means is you can have like a smaller core dump. So maybe only like a few kilobytes instead of like 256 kilobytes. And it optimizes for both on-device storage as well as bandwidth. So yeah, I would say Zephyr and FreeRTOS we have really, really good support for. And the other ones you'll generally see support for. And if you're using something a little more niche, just email us at support@memfault.com and we'll be happy to answer if we have support or not.
Awesome. We also received a question on using Memfault with satellite connected devices. And I do believe that we have a customer who is actively using Memfault with a satellite link.
Yeah, it's definitely supported. Obviously, like bandwidth is like pretty pricey on those systems. So when we have customers that have like really tight bandwidth budgets, we work pretty closely with them to optimize the amount of data that's sent up. So maybe we only send up like a very minimal, report that the device crashed. And then if you want like a more detailed core dump, maybe you have to like, send a command down to the device saying, hey, send the full data up. And that way you make the best use of your bandwidth without like, really overrunning your budgets on a per device basis. How much data was retrieved from the device to generate that core dump? We clicked through several core dumps, but the ones we were showing today were generally on the order of, I think something like 10 to 30 KB for the NRF52 side of things. And then the ESP32s, because they're Wi-Fi connected, the default implementation will store, whatever you've allocated for the core dump partition. And that could be like, 256 KB, I think is pretty typical. But because you have that Wi-Fi link, of course, things are a little more friendly to the large core dumps. Oh, I should point out, though, that's fully under your control, how much space you want to allocate on the device for the core dump. So if you only want to allocate like 1 KB, you'll still get like a nice backtrace. You just won't get all that global and static, variable breakdown.
Yeah, and sort of to piggyback off of that, we have a similar question of asking like, what's the minimum recommended resources for Memfault to capture? And for this question, I would say, depends on your use case. We would recommend, on a system running an RTOS, usually around a kilobyte is required because we want to try and capture as much of the active stack, the stacks of each of the tasks that are running, the state of all those tasks, as well as we might need to capture some additional structures in memory, particularly in the FreeRTOS case, when you have dynamic tasks, we have to get some memory that's only in the heap region.
Nice. A couple of questions around like sort of resource usage in terms of CPU as well as like memory footprint and that sort of thing. Yeah, memory footprint, the overhead of the library itself is 4.5 KB flash, about 1 to 1.5 KB RAM. But that's under your control. If you like remove a few components and squeeze that down a bit, that's certainly possible. And it can grow depending on if you're integrating with like more sophisticated like Zephyr logging backend and that sort of thing. But those are the numbers that we usually see on an integration. And then in terms of performance impact, this one is really nice because by default, the Memfault SDK won't be running at all by itself. So there's no performance overhead until a crash occurs. And that's when our fault handler kicks in and does that saving of memory, et cetera. But if you do enable the metrics component, there will be a periodic task that you'll want to enable to like capture that heartbeat. So maybe like every hour you'll run a small function. And that's on the order of like a few hundred cycles typically, but it's fully under your control. So if your device has really tight battery requirements and needs to sleep for like 6 hours at a time, totally reasonable thing to do. You'll just increase that heartbeat interval there.
We've got a couple of questions around debugging symbols. So they're kind of asking, what are the requirements on debugging symbols? And the answer is yes. All that information that you saw on our core dumps is coming from those debugging symbols in your ELF. The binary that you send to the device is not required to have those in there, but we do need the symbol file that is generated from your build to be able to collect all this information.
Yeah, so a lot of IDEs will when you set up your template project, it'll have like a debug and a release configuration. We sort of recommend not splitting those, or rather just running one configuration on your desk that you also ship to your devices. So same compilation flags, enable debug symbols on both, since there's no overhead, and then you can, overhead on the device itself, I should say. Those debug symbols aren't loaded on the device, like Eric said. And then you can have the same exact, optimized for space or optimized for speed or whatever, running in production as well as like on your desk, which makes things like that very nice, I think. Are the demo apps shown here available? Great question. So yes, all the demo apps we showed today are just the ones that we have either in the Memfault firmware SDK repository itself under the examples folder, or the only exception is the peripheral MDS example that I showed. So that's in the Nordic Connect SDK under the examples folder, I believe. This is a question I love. Would you use Memfault to monitor development systems? Yeah, it's really, I think Memfault really, it's great for fielded devices, but then you're getting like a lot of data in, so it can be a little like more difficult. And that's why we have those tools for like filtering like most frequently reported issues, et cetera. In terms of like development systems, when you're doing like bench testing or like maybe you've got some devices in a lab or doing some beta test, Memfault is really amazing because it's giving you like very, very detailed like crash reports anytime the device hits an error, and particularly when you're in like that early development phase. Maybe the system's a little more rough, like some features aren't quite filled out, or you haven't like tested it against like all the weird scenarios like connection times out or packet loss, that sort of thing. So yeah, it really shines in that early development process, and typically then you have a lot of people like QA team, engineering team, all with their eyeballs on those Memfault dashboards, which is great.
We have a couple questions on the task watchdog, asking about the configurable, if there's a configurable timeout value for each task, or what happens if you have a task that is running for a while and it's supposed to be doing that, or maybe it's supposed to be blocked. The task watchdog API provides methods to start and stop the watchdog. So what you can do is you're going into this state where this task is going to be blocked a while. You can stop it just for this specific task. That way, the task watchdog is still monitoring for everything else on your system. And then, once this long-running thing resumes, you can start it back up again for this task. And then we also, provide a way to feed the watchdog every so often. So you can programmatically add that in where you need it to.
We had a question come in from the webinar registration. So how exactly does Memfault help catch bugs sooner? How is it better or unique compared to other code analyzers? This is actually a very good question. So we don't, Memfault's solution is around like sort of runtime or like debugging or capturing performance data on the device itself. Whereas a code analyzer, like a static analysis check, that would be something you would like run against your code base. And whether that's like Clang static analyzer or, even something like the old like linter like options or clockwork, like other security type static analysis tools. I think it's really good to like use as many tools as you can. So running a static analysis tool is awesome. It's going to like probably pick up, a lot of like programming errors that you wouldn't want to like get to your device, like null dereferences and stuff like that, that are actually like evident in your program, statically. But Memfault and debugging in general is really nice on the fielded devices themselves because it takes into account like all the hardware constraints. Like maybe you hit like a brownout condition, and a static analyzer isn't really going to help you detect that sort of error. So yeah, hardware devices experience a lot of weird failures, and Memfault really shines there. We have another question here that I love. So does Memfault extract private data from the core dump? Does it have like security implications, etc.? So Memfault is it's a read-only system, so data only flows from the device up to Memfault, except for the Memfault's OTA system, which we didn't show today. But in that case, the device is also in control of the download of the OTA payload. So you're in full control of what data elements get uploaded to Memfault, and we help you, and we have guides on our docs page as well about like excluding private or sensitive information from the core dump data. It's very easy to mark a region as like don't collect or that sort of thing. And we can also scrub data after the fact, but everything's encrypted on our cloud. There's separate encryption buckets for all our customers and that sort of thing. So take it very seriously. Obviously, IoT security is not a joke. So it's very very high on our list of concerns.
Quick question, just to answer this one really quickly. We do support the NRF5 SDK because I believe that runs with VRTOS. Just to answer that one. And then we have a couple of questions around, how do we require sending events or logs as they happen immediately? Can they be batched? And the answer for that is that they can be batched, or they can be sent up, as whenever you need, really. We do have some rate limiting around metrics and logging just to keep our system stable and prevent abuse. If you're operating a device that has a real constrained bandwidth, we definitely recommend batching that up to suit your links needs there.
A couple other questions. Have you detected many problems in the Memfault code using Memfault? Yeah, we certainly have. We're not proud of our errors that we ship, but the nice thing about the Memfault platform is when an error occurs, whether it's in the Memfault code or some other piece of the application, it gets snapshotted in a really great way. It helps us, and we're in the position when debugging the Memfault code itself. That our position is similar to like a field applications engineer for a vendor. And we do partner with like Nordic Semiconductor, Texas Instruments, a couple other like silicon vendors, and their FAEs really like our platform because a customer that experiences a crash, whether it's in like the vendor SDK code or the application code itself, they can send the core dump to the FAE, and that FAE has a really great set of information for diagnosing problems.
Yeah, I can personally speak of a bug that I found while working on our SDK in around heap tracing. There are certain RTOSs that actually allow allocations from ISRs, and when I was prototyping it, I had the wrong type of locking in place that was not allowed in an ISR context. So quickly caught that with Memfault, but a little bit of a tricky one to find because it's not something I normally do when I'm writing code.
Another question here, can you visualize the Memfault data locally, offline, or is it only analyzable by the the web app or the online platform? So the data does have to be sent to Memfault for analysis. So we'll run our backend will run like all the processing on it and generate all the reports and whatnot. But once that's done, you can then download the core dump data and load it into your like debugger locally, and it is a post-mortem but semi-interactive sort of way, and then you can poke around at all the data. We also have a pretty rich API that you could use for extracting various bits of data. Everything you saw in the web app is available over our API. So yeah, you can, once the data has been analyzed by our system, you can suck all that process data down and do your local analysis. Are we doing on time? A few more minutes. All right, let's see, anything else? I think that's it for the, oh, okay, here's one more that I'd like to cover. My bundle variable length application-specific binary data with a Memfault device failure report. So yes, you can. We have a recent feature that we call custom debug reports. And that feature enables uploading arbitrary binary data. It'll show up similarly to like the log data that Eric was showing in the timeline view. And that's a really neat feature. It provides you like the ability, for example, if your like modem, your modem chip provides like some trace data or some sort of like crash reporting and stuff like that in a weird format that you can't parse like yourself, or at least not on the device. You can then just snapshot that data, that raw binary data, shoot it up to the Memfault cloud. And then, after the fact, you can go and see, okay, there was this crash, there's this attached like CDR report data. Download that, run it through like Wireshark or whatever like tool you need to, and it'll give you like a really nice detailed like analysis feature essentially of your specific device. And yeah, very flexible tool. So I highly recommend checking it out if that's something you're interested in. All right, I think we're just about out of time.